Hello guys, welcome to Victor Learning. Okay, there's actually four parts to this corrosion that I want to share with you all. First part will be this video, the dry part, dry corrosion, the wet corrosion, and the types of corrosion, as well as corrosion prevention. Okay, so let's go. Okay, topic one. Today I'll cover what is exactly dry corrosion and the oxidation principle and free energy that governs the oxidation mechanism, type of oxide, and PBR ratio, as well as the three reaction laws that I will cover: linear, parabolic, logarithmic, and some introduction to the metal gas reaction. Okay, what is dry corrosion? Dry corrosion is actually oxidation. What is oxidation? Oxidation is actually when there's a reaction of material with the environment or oxygen to form oxide layer on the material. Okay, this usually occurs during when the relative humidity of the environment is lower than 60%. As for the wet corrosion, it happens above 60% to 65, above 60%, yes. And the chemical reaction are as follows. The metal react with the oxygen plus the energy will turn into oxide. So for reaction to proceed, right, metal will actually become ionic form, whereby ion turn to ionic form and give out electron and react with the environment. Okay, what is free energy principle? Is actually denotes at delta G. It's actually the thermodynamic principle that tells you the reaction feasibility of the particular material, whether you will form oxide or not, but it will not tell you the rate of the reaction, so do not get confused. It might be what some part of the question. If you are taking corrosion engineering, this might be tricky, and this is a function of temperature. Therefore the free energy will go up or down depending on the temperature. So what's so important about delta G? Okay, when delta G is 0, less than 0, reaction will proceed, meaning the metal will form oxide by itself. So when delta G is more than 0, reaction will not proceed, meaning that the metal will not form oxide layer. So from this example, iron delta G is negative 508 kJ per mole, means it will form oxide. But as of gold, delta G is positive 80 kJ per mole, so it will not form oxide. It's actually that simple. So what is oxidation mechanism? It's actually a diffusion of electron across three potential interface reacting with the environment to form oxide. It can form at the metal oxide layer, oxide layer, oxide oxygen layer. Oxide oxygen is here. Okay, oxide is here, and metal oxide is here. Okay, so it depends on the oxide thickness. If the thicker oxide layer material form, it will be harder for the electron or oxygen ion to travel across. It's actually correspond to this Regular law. So also just now I mentioned that this temperature also plays a part. So if it is a higher temperature, you increase in the ionic diffusion and increase the corrosion rate. So what are the type of oxide available? Okay, we can see. Okay, adherent, non-adherent, and volatile. Adherent is sticks well and have tight bonding between the oxide and the material. So this is protective oxide. Okay, for non-adherent, I mean, as the name says, so it does not stick well and allow diffusion of oxide layer easily. Volatile, this kind of oxide is not protective and it actually evaporates when formed. So what is Pauling backward ratio? It actually indicates the oxide layer are likely to be protective or not. So if it's less than 1, it's not protective. If it's more than 1 and in between 1 to 2, it's protective. But for PBR, more than 2 is not protective due to excessive compression stress. Even having said that, for PBR 1 to 2, it indicates the oxide layer is protective, but it also must be defect-free and stick well to the surface during application to be truly protective oxide. So there are some reaction law. It governs the rate growth of films, the oxide film. For linear law, it's actually for PBR ratio less than 1, more than 2, meaning that this is not protective oxide, as the growth of the oxide layer is proportional to time. The oxide will keep growing and growing and growing. If the oxide layer is protective, it will stop at a certain point. But for this case, it's not. So example of this kind of material is alkaline earth metal. Magnesium is one of them. So for parabolic is actually protective. Okay, meaning the oxide will stop at this point. Once it reaches the protective stage, formation of oxide will stop over time. You see, this part they will stop. Okay, such example is like iron, copper, and nickel. Logarithmic. Logarithmic is actually describe oxide that is very protective, such as aluminium Al2O3 is actually very protective during dry condition. So you see, and other laws such as cubic and inverse logarithmic will not be covered here. If you are interested, you can go and Google about it. So, metal gas reaction. So when metal react with oxygen, you will form oxide. But when you react with sulfur, you will actually form sulfur scale that is not good. So when there's sulfurization, is actually when the metal react with the environment that contains sulfur, is such as coal power plant. Okay, this kind of metal, nickel and nickel rich alloy are actually very skeptical toward this kind of attacks. Second attack, halide attack is due to the presence of fluorine or chlorine that will cause halide attack. The third attack is the hydrogen attack, meaning whereby the hydrogen diffuse into the metal and decarbonization, meaning there's a reduction in strength. It only happen for crystalline along grain boundary and reduction in strength, formation of hydride, and grain boundary embrittlement. So this kind of plain carbon steel or high strength steel under no oxygen, no high temperature actually are most likely to be subjected to this kind of attacks.